Imagine a busy warehouse where hundreds of items need to be collected and restocked every hour. Traditionally, this relied on humans, but labor shortages, safety risks, and mistakes make this process slow and unreliable. Meet Team 23's autonomous restocking robot. 4 intelligent subsystems, navigation, vision, item collection, and mobility work together seamlessly. It can locate the correct station, identify the right item, and deliver it precisely to the correct bay faster and more reliably than a human could. In this video, we'll show you how a robot transforms warehouse logistics into a seamless, safe, and ultra-efficient operation.
Hi, I'm Hannah and I was responsible for item collection. The item collection subsystem needed to repeatedly collect and place items onto shelves at various heights. Item collection was split into 2 parts, the gripper, which collected the items, and the lift system, which controlled the height of the gripper. The final gripper design was a 4-bar linkage system controlled by a microservo. The crossbars ensured that the end pieces of the gripper always remained parallel. This way, the gripper always made even contact with 2 sides of the item, regardless of its size or shape. A microservo was used because it has positional feedback that regular DC motors don't have. This made collecting and placing items much easier, as servo positions could be used instead of timings. The lift system was inspired by the design of a forklift. It consisted of 3 nested frames connected with string to a shaft under the robot chassis. This shaft was controlled by a 12-volt DC motor that either lifted or lowered the gripper depending on the direction it was run. The item collection subsystem was integrated into the robot by securely bolting it to the chassis, so it would remain in place during use but could also be removed for maintenance. The gripper and lift system were both 3D printed out of PLA to minimize the weight of the subsystem.
To complete its desired functionality, it requires a stable and reliable movement platform and allows all other components to operate from a consistent platform. My name is Lucas and I'm responsible for the design and implementation of the mobility system for this robot. The chassis was designed 3 meters seconds to increase the modularity of design as shown in the animation below. The main chassis consisting of track, drivetrain, and item collection lift shaft. The control box situated at the back of the robot consisting of all electrical components, the Raspberry Pi and camera. And lastly, the item collection system base mounted to the front and also containing the battery and lift motor. The separation of the components in this way was to enable subsystems that could be independently removed and serviced without complete deconstruction. The drivetrain of the robot was decided to consist of a skid steer track platform, as this was determined to be the most effective for the requirements of the task. This solution was chosen due to its traction, stability and confined conditions, which will allow it to traverse the inclines and rotate within the small aisles present in the warehouse. On the software side, open loop velocity control with acceleration limiting and safety watchdog times was implemented. This results in predictable, repeatable motion for alignment to reference points.
Hi, I'm Kisok Won, in charge of the vision system. Just like we use our eyes to recognize objects and decide how to act, the vision system helps our robot understand and respond to its surroundings. The system uses HSV to process colors, hue for color type, saturation for intensity, and value for brightness. This method makes color detection more stable even when the lighting changes. The robot identifies items, stations, shelves, obstacles, markers, and walls. Once objects are detected, the system calculates their bearing, how far to the left or right they are, and their range, which is the distance from the robot. Distance is estimated in 2 ways, by comparing the object size in the image to its actual size, or by checking where it touches the ground in the frame. The system runs on board at over 10 frames per second, providing fast and reliable data for decision making.
What makes a robot fully autonomous is its ability to coordinate perception, decision making, and action in real time. My name is Ayana and I'm in charge of the navigation subsystem. It serves as a central coordinator. It receives real-time vision data and converts this into mobility commands, controlling forward and rotational velocities to accurately navigate through the warehouse. A reactive approach, governed by a finite state machine, ensures the robot can dynamically respond to the environment, such as activating the item collection at the correct stations or bays. Importantly, no timers are used to enforce alignment, ensuring consistency in navigation. Proportional control provides smooth alignment to markers without the complexity of full PID tuning, while the LED status board provides clear visual feedback of the robot's current task. While obstacle avoidance hardware remains to be deployed, the potential field algorithm is fully operational in hardware-in-the-loop simulation. All subsystems, vision for object detection, navigation for calculating optimal paths, mobility for transport, and item collection for safe pick and drop are fully integrated, validated, and ready for deployment. Thank you for listening, and at Team 23, we're prepared to launch a system that defines the future of warehouse automation.